Hello, my name is Cameron Castles and welcome to my video presentation for MATH3032 Topology and Analysis. In this presentation I will explain the Epsilon-Delta definition of limits and demonstrate some proofs that illustrate the concept. In calculus, the notion of limits and continuity arise and are taught to us in ways that are quite vague and rely largely on our intuition. We are taught that a function f of x has a limit L at a point P if f of x approaches L as x approaches P. We are also taught that a function f of x is said to be continuous if it has no gaps or sudden jumps in its output. And mathematicians really relied on these notions up until about the 19th century, when the field of analysis started to come about and it was clear that a much more rigorous definition of limits and continuity would be required. In the early 19th century, mathematicians became interested in developing the soundness of calculus so that important theorems could be proved with sufficient rigor. For example, the intermediate value theorem. Bohemian mathematician Bernard Bolzano and French mathematician Augustin Louis Cauchy both illustrated the basic arguments of the Epsilon-Delta definition, but it was Carl Weierstrass who fully realized the concept in its modern form in 1861. And for this he is often called the father of modern analysis. So the epsilon-delta definition of the limit goes as follows. For the limit as x approaches x0 of f of x, which equals L, we say, for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of the difference between x and x0, which is less than delta, then the absolute value of the difference between f of x and L is less than epsilon. We'll take a look at what this means graphically. So as you can see, what this definition generates is a sort of box around the limiting points of dimensions 2 epsilon by 2 delta. And what it means for the limit to exist at point x0 is that you can pick a epsilon such that there will always be inputs within the range of delta that correspond to outputs in the range of epsilon. Now the key here is that epsilon can be arbitrarily small around the limiting point. And what it means for the limit to exist is that no matter how small epsilon gets, there will always be a range of inputs within delta that correspond to outputs in epsilon. Here we have an example where we can intuitively see that the limit does not exist, because as you approach x0 from the positive and negative directions, the value that it approaches is different, therefore the limit is undefined. But the epsilon-delta definition helps us quantify why this is true. As you can see in this discontinuous example, we can choose an epsilon that is sufficiently small such that within the range of deltas there will be outputs that are outside the range of epsilon. So by the epsilon-delta definition, the limit does not exist at x0 on this function. I will now demonstrate a couple of examples that show how we can use the epsilon-delta definition to prove a limit. So here we have the limit of 3x plus 1 as x approaches 2 is equal to 7. Now, how we're going to prove this limit is by using our definition, which again, for all epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x take x0, which is less than delta. Therefore, the absolute value of f of x take L is less than epsilon. So, we know that in this case x take x0 is x take 2. So we suppose that the absolute value of x take 2 is less than delta. Now, we know f of x take L is 3x plus 1 take 7. which we want to algebraically rearrange into terms of AL less than delta, so that we can cancel it out to epsilon and show that it is less than epsilon. And we'll choose a strategic delta to show this. So we can arrange our 3x plus 1 take 7 to 3 times the absolute value of x take 2, which is our less than delta term. So if we pick delta to be epsilon over 3, this cancels out to epsilon and completes the proof. So that's what we do. Given epsilon is greater than 0, we choose delta equals epsilon over 3, and suppose that 0 is less than the absolute value of x take 2, which is less than delta. And we check that the absolute value of 3x plus 1 take 7 is indeed less than 3 delta, which is equal to epsilon. Thus it is shown. For this next proof, our method for choosing delta is a little more involved, but it's not much harder. Here we have the limit of x squared plus 3x plus 1 as x approaches 2 is equal to 11. Now, we again suppose that 0 is less than the absolute value of x take 2, which is less than delta, the same as our last proof. Now, our f of x take L term is, in this case, x squared plus 3x plus 1 take 11, or x squared plus 3x take 10, which we can factorize into absolute value of x plus 5 times the absolute value of x take 2. Now, there's our delta term, the absolute value of x take 2, but the x plus 5 is an issue to us. Now we can see that x take 2 is less than delta, which is clearly less than 1. Now, if we add 7 to that, we can get x plus 5 is less than 8. So we know that x plus 5 times x take 2 is less than 8 delta. If we choose delta to be the minimum of range 1 through epsilon on 8. So our proof goes as follows. Given epsilon is greater than 0, we choose delta equals the minimum of 1 through epsilon on 8, and suppose that x is less than the absolute value of x take 2, which is less than delta. We check that the absolute value of x squared plus 3x plus 1 take 11 is equal to the absolute value of x squared plus 3x take 10, which we can factor to the absolute value of x plus 5 times the absolute value of x take 2. This is less than 8 times delta, which is equal to epsilon. Thus it is shown. We can use the Epsilon-Delta definition to help us prove the continuity of a function. A function f of x is continuous at the point x0 if the limit exists at x0. This is because if the limit isn't well defined at a point, there must be a discontinuity at that point which disallows the taking of a limit, as I showed before. So to prove f of x is continuous everywhere, we prove that the limit exists everywhere by taking the general case. The following is an example of how we can use the Epsilon-Delta definition to help prove the continuity of a function. So our conjecture is that f of x equals x squared is continuous, and the proof is as follows. We fix epsilon is greater than 0 and observe that the absolute value of f of x take f of x naught is equal to x squared take x naught squared, absolute value, which by the triangle inequality is equal to the absolute value of x plus x naught times the absolute value of x take x naught, which is less than or equal to absolute value of x plus the absolute value of x naught times the absolute value of x take x naught. If the absolute value of x take x naught is less than 1, then the absolute value of x take the absolute value of x naught is less than 1. So the absolute value of x is less than the absolute value of x naught plus 1. Hence, if the absolute value of x take x naught is less than 1, then the absolute value of f of x take f of x naught must be less than or equal to 2 times the absolute value of x naught plus 1 times the absolute value of x take x naught. Using this, we let delta equal the minimum of 1 to e over 2 times the absolute value of x naught plus 1. Then, if the absolute value of x take x naught is less than delta, the absolute value of f of x take f of x naught is less than or equal to 2 times the absolute value of x naught plus 1 times the absolute value of x take x naught, which is less than or equal to 2 times the absolute value of x naught plus 1 times the epsilon over 2 times the absolute value of x naught plus 1, which of course is equal to epsilon, thus showing that x squared is continuous via the epsilon-delta definition. Uniform continuity is a very similar concept to continuity and is defined quite similarly. We say that f of x is uniformly continuous if, for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of x take y is less than delta, therefore the absolute value of f of x take f of y is less than epsilon. The key difference here is that delta can only depend on epsilon, as opposed to, say, the previous proof where delta was also dependent on x naught. So the function f of x squared, f of x equals x squared, is not uniformly continuous over the reals. X squared may be uniformly continuous over a smaller interval, however. The following is a proof of this. Our conjecture is that f of x equals x squared is uniformly continuous on the interval, open interval, 0 to 1. So we fix epsilon is greater than 0, and observe that the absolute value of f of x take f of y equals the absolute value of x squared take y squared, which is equal to the absolute value of x plus y times the absolute value of x take y. And since that term is positive, we can make that equal to x plus y times the absolute value of x take y, which is less than or equal to 2 times the absolute value of x take y. Using this, we set delta equal to epsilon over 2. Then, if the absolute value of x take y is less than delta, the absolute value of f of x take f of y must be less than or equal to 2 times x take y, which is of course less than or equal to 2 times delta, which is equal to epsilon. Therefore, f of x equals x squared is uniformly continuous on the open interval 0 to 1. Thank you for listening to my video presentation on the epsilon-delta definition of limits.